We see how the sky is full of stars. Among them, one stands out as the brightest. It's so bright that it provides not only light but also heat to nearby planets. You've probably guessed it already. Yes, we're talking about that massive glowing ball of fire we see every day when we wake up. None other than the sun. We're sure you know that the sun is at the center of our solar system. But did you know that it's also the star with the strongest gravitational force that holds our solar system as a whole together? It's so powerful that everything from the most giant planets to the tiniest particles orbits around it. Also, we all know how massive the sun is, but did you know that it's so huge that it could easily fit about 1.3 million Earths inside it? I bet you've heard about all of this before, and it's just been sitting at the back of your mind. Well, guess what? In this video, we're going to bring you some exciting discoveries and information that you've probably never heard of before. Now let's talk about how the sun came into existence. According to scientists, it all started with a giant cloud of dust and gas that formed roughly 4.5 billion years ago. This cloud eventually collapsed under the force of gravity, causing it to spin and flatten into a disc-like shape. As time passed, the center of this disc became denser and hotter, eventually giving birth to our sun. Furthermore, the sun's gravity and pressure at its core are so intense that it causes a process called nuclear fusion. Essentially, this is where hydrogen atoms fuse to form helium, releasing a massive amount of energy in the process. This energy is what gives the sun its radiant light and extreme heat, which ultimately influences the environments of all the planets, moons, asteroids, and comets in the solar system. There's a lot we know about the sun, but it is outweighed by what we don't know about it. Despite the sun being one of the most influential elements in our universe, there's still so much we don't know about it. However, recent discoveries have allowed scientists to better understand the sun's composition and the various layers that make it up. The core. First off, there is the small but super dense part at the center called the core. It's only about 20 to 25% of the sun's size, but it's extremely hot, with a temperature of around 15.7 million Kelvin and a density of 150 times that of water. This is where most of the sun's energy is produced through a process called nuclear fusion. Basically, hydrogen is converted into helium, which generates a ton of energy. In fact, the energy produced in the core is what powers the sun. Hence, the core is the main source of thermal energy, generating a whopping 99% of the sun's power. Only about 0.8% of the sun's energy comes from another process called the CNO cycle. This energy then moves outward through the sun's various layers, such as the photosphere, before eventually escaping into space as radiation or massive particles. Despite the huge amount of energy being produced in the core, the fusion rate is actually in a self-regulating balance, which ensures stable energy production. The sun's energy output is equivalent to 4.26 million metric tons per second. That's a lot of power. However, due to the core's large size and density, the fusion rate is balanced out perfectly. The radiative zone. After the core, there's the radiative zone, which is the thickest layer of the sun. It starts from the core and goes up to about 0.7 solar radii. If that doesn't give you a proper estimate, the fact that a single photon of light can take more than 100,000 years to travel from the sun's core to the outer boundary of this layer and into the next region, which is the convective zone, definitely will. But how is energy transferred in this zone? Through thermal radiation. The temperature here is pretty high, ranging from around 7 million to 2 million kelvins. As we move away from the core, the temperature decreases, and this creates a gradient. However, the gradient isn't abrupt enough to cause convection, which is the transfer of heat through the movement of fluids. Instead, energy is transferred through radiation. The ions of hydrogen and helium in the radiative zone emit packets of light energy known as photons. But these photons don't travel far before they're absorbed by other ions, creating a bouncing and colliding effect. This bouncing around of photons and their interactions with nearby gas molecules is how energy is transported through the radiative zone. As we move further from the core, the density in the radiative zone drops significantly, which means that the material becomes less dense as you move outward. The connective zone. The next layer of the sun is called the convective zone and starts about 500,000 kilometers away from the center of the sun and goes up to the surface. This layer is responsible for transporting the sun's internal heat energy outward towards its surface. However, the sun's heat is not transported through radiation but through something called convection. Since the plasma in this layer is not tightly packed, this means that the hot plasma in this layer moves in currents, carrying the energy from the sun's interior to the surface. As the heated material diffusively and radiatively cools just beneath the photosphere, it becomes denser and sinks back down to the base of the convection zone, where it once again picks up heat from the upper part of the radiative zone, and the convective cycle continues. This movement creates a texture on the surface of the sun, which looks like bubbles of several sizes. The convective zone is like a big engine that keeps the sun's energy balanced and stable. The photosphere. Up next is the photosphere, which is the visible surface of our star. It's the part that shines and radiates light, and it's where sunlight comes from. The photosphere is not a solid surface, but a thick layer of hot plasma. It's thinner than the Earth's atmosphere, so it's not very unclear. Interestingly, the photosphere is hotter at the bottom and cooler at the top, which causes the edge of the sun to appear darker than the center. When we see sunlight on Earth, it's a mix of light and energy that comes from the sun. Lastly, the photosphere also played a big role in discovering the element helium, which was first found in the sun. The chromosphere. The next layer of the sun is known as the chromosphere, named after the Greek word chroma, which means color. During total solar eclipses, this layer shows beautiful colors at the beginning and end. It's about 1,250 miles thick and is full of exciting things to see, like spicules that look like fiery gas jets. These spicules can extend for thousands of miles before disappearing, which makes for a stunning view. What's particularly impressive about the chromosphere is that it gets hotter the higher up you go, unlike the inner layers of the sun that get cooler. In fact, temperatures in the chromosphere can get as high as 20,000 Kelvin near the top. The corona. No, this has no relation to the coronavirus of 2020. This one is the outermost layer of the sun. It was actually named after the Latin word for crown because it looks like a glowing crown around the moon during an eclipse. This one is a thin and delicate layer that surrounds the sun. It's so big that it stretches for millions of miles, but we can only see it during a solar eclipse or special X-ray images. The corona is very hot, even hotter than the sun's surface. Scientists are still trying to understand why it's so hot. But they know that the sun's magnetic field is really important for corona's behavior. This magnetic field causes things like solar wind and solar flares, which can affect the corona and Earth's magnetic field. But what are solar winds? The sun releases streams of tiny charged particles, mainly electrons and protons, that are ejected from the corona. These particles are known as the solar winds, and these winds carry energy and magnetic fields from the sun into space. They can impact the behavior of planets and other objects in our solar system. Because planets with magnetic fields like Earth have something called magnetospheres. When these planets are hit by solar winds, it can cause a few different things to happen. One of the most beautiful effects is the creation of auroras, but it can also have some not so great effects too, like compressing or distorting the planet's magnetosphere, which can lead to changes in radiation belts and magnetic field strength. And if a planet doesn't have a strong magnetic field, solar winds can even strip away its atmosphere over really long periods of time. That's actually what happened to Mars and Venus, and it's probably why they lost their atmospheres. In the last couple of years, some scientists got their hands on advanced instruments and extended fields of view to make first-of-their-kind observations of the middle corona in extreme ultraviolet wavelengths. That's where they found that solar wind structures originate in this region and also found a complex plasma network in the middle of corona. Recent discovery. Other than that, there was a discovery by NASA. That is the reason we have as much info about the sun as we do. Their Parker Solar Probe went on a mission to explore the corona and found some really interesting things. By gathering samples of particles and magnetic fields in the corona, scientists learned about the sun and its effects on our solar system. These findings also helped us understand more about the sun's magnetic field and how it affects the solar wind. Plus, they even discovered the origin of magnetic zigzag structures in the solar wind called switchbacks. Thanks for watching our video. We hope you enjoyed it and learned something new. We'd love to hear your thoughts and questions, so please share them with us in the comments below. And if you want to see more videos like this, hit the thumbs up and subscribe to our channel.